Hi students, am I audible ma? Hi students. Okay, I hope we can start another session. Okay, so if I'm getting disconnected or any issues, na, just ping me a message and watch it. Okay, so good evening, viewers. In today's session, we are about to discuss. Just a moment. Okay. So good evening all. So in today's session, as I have informed you already, we are going to discuss about your magnitude comparator alone. So which comes under your unit 2 of your combinational circuits. Okay, so with that note, we will move into it. So this session would be helpful for both the set of students, like those who are learning digital electronics as well as those who are learning DPSD. Okay, so with that note, I will move into the session. So for any digital electronics or the digital principal system designs, that is CSC, AI ideas, or any department students, something involving your digital electronics, now unit 2 will be always your combination circuit design. So under unit 2, you will have the following topics, like starting with your adder, half adder, full adder, half subtractor, full subtractor, and the binary parallel adder, carry lookout adder, BCD adder, and these two adders, carry lookout adder and BCD adders, are the fast adders for you. Okay, and to build these, you should know the basic how a 2-bit addition happens, and to perform that, what is a circuit. So that is what we call it as a half adder. And if you have a carry to be generated from the previous addition, uh, along with the present set of two input bits, how to add the carry generated bit, so that we call it as a 3-bit addition, so that we once again name it as a full adder. Okay, so this is how the same applicable for your subtraction also. Then you have data transmission circuits like multiplexer, demultiplexer, and magnitude comparator also comes under your arithmetic operation. Okay, and finally you have a decoder, encoder, priority encoder, and also you have something called code converters. In this session I didn't include, wherein in later sessions I'll come out with those topics. Okay, so as I've told you, today we are going to deal with your combinational circuit. So what is all about your combinational circuits? As I've informed already, just a moment, I'll increase the volume. As I've informed already, combinational circuit is nothing but is one of your logical circuit, because as you all know, in your starting of the session in your classroom in person, I've discussed about I've given a introduction on your logical circuit, why the name logical circuit, everything. And its types are, basically we have combinational and sequential. Under combinational, why it is called as a combinational circuit, what makes the difference between a combinational and a sequential now? Here a circuit, logic circuit, which combines all your basic gates, or special derived gates, or your universal gates, all those circuits will perform its operation for the instantaneous inputs and produces the output instantaneously. That is why they call it as a combination circuit. Okay, we don't store anywhere or we don't retrieve back any of the processed data, and we don't use it for further operations. Okay, so those circuits which does or which receives the instantaneous input and process it and produces the output, those we call it as a combinational circuit. Okay, so any circuit, as you all know, you will have an input and you have a gates, set of gates to perform the operation for whichever the logic you intend to design and you want to bring out the output. Okay, so always any circuit will have, any logic circuit will have input, output and the gates to perform the operations. Okay, so that is what we have given here. It consists of input variables, logic gates and output variables. Example circuits, as I have discussed already, we have n numbers, but here we have listed few: encoder, decoder, marks, demarks. Okay, so now what is a block diagram of it? Now simply you can put a block like this. This speaks about any circuit, and these are the multiple inputs and these are your one or more outputs. Okay, simply speaking, multiple outputs. So this is your simple block diagram. And if you want to characterize now, as I've told you, instantaneously it will receive, it will instantaneously produce the output. It doesn't make use of any memory to store and retrieve back later for future use. Okay, as we do it in memories and all. Okay, that also comes under digital, but those circuits are will come under your sequential circuits. So combinational circuits are the one which receives instantaneous inputs and produces the instantaneous outputs, whereas sequential, it will get the, or a part of your output will be taken back and it will be processed along with the present set of inputs. So there will be a feedback path in your sequential circuits, which we will learn it in detail under your third unit. Okay, so there, since we have to take it back and we have to process with the current set of inputs, there we will make use of memories or delay elements. Okay, so that we call it as a sequential circuit. So today, in today's session, we are involved with your combination circuit, so we will concentrate in that alone. So as I've stated already, combinational logic circuit, broadly the circuits could be classified under three categories. Any circuits performing arithmetic operation or any specific logical functions, now you can categorize under arithmetic and logical function circuits. Okay, that is one type. Or any circuits which is merely used for data transmission alone. Whatever is given inside the circuit, you can simply transmit to the other end. So mostly whatever the circuits you are going to see under this classification, or the circuits which plays a vital part in your networking, because nowadays we transmit, receive through wireless also. So remember how important these circuits and all. Okay, so wherever routers are there, you will have all your encoders and decoders, everything to be playing its important role. Okay, and even multiplexes and demultiplexes, your telephones. Even in BSNLs earlier, they had all these things. When you go for your industrial visit, they will show you this, how to select a particular line and how it is being. So multiplexers, you know, they call it, again, the other name is what? Data selector and data distributors. These two are. Okay. So all the circuits which just transmit and receives the data, those circuits could be categorized under this classification. A sample circuits are given here. So here we have categorized based on the syllabus. Okay. And other than these two, that is performing arithmetic and logical function and data transmission, you have something called code converters. That is, one form of data is converted into another form. So those circuits also could be categorized under a combinational circuits under the, specifically under the category code converters. So what are they? Binary to BCD code converter, BCD to binary, and BCD to 7 segment display. Got it? And actually speaking, BCD to 7 segment could be categorized as one of the application of your decoder, and also could be categorized under code converters for your information. Okay, so in some of your books, in some of the authors' books, under decoder topic only you will see your BCD to 7 segment. Okay, in certain books you will see the under code converters. It could be applied to under both the categories. It could be acting as an application for a decoder, and it could be categorized under, because one form of your data is being converted into another form. Why, how, and all I will explain in detail when we are discussing about specifically about code converters. Okay, so just get to know. Usually for sequential you have two types, asynchronous sequential and asynchronous, whereas under combinational they don't categorize mostly, but you have further classification for your information. You can categorize based on the functionality of the circuits. So if it's performing arithmetic functions now, under the first category, if it's just transmit and receive now, data transmission circuits, or if it is converting one form of data into another codes now, then so why specifically the code converters now? Because you know, you learned your codes. What are the different? You have positive code, negative codes. Under positive codes, you have 8421 code. 8421 is a code. 8421 is used code, that code only is used for BCD representation, and the extensions of that, that is 8 1 2 4 8 16 32 64 128, we just listed based on 2 power n, no, so that because that is also one set of codes which could be categorized under binary. To represent a binary value, it is 2 to the power of n. So how many of a value, that is whatever the value you want to represent, those many bits would be used. Okay. As 7 segment na, based with the help of a 7 segments, just we human beings will the best example for a 7 segment is what na, a calculator. In your calculator, you will see 10 to 12. First, earlier, the 4-bit nimble calculator, 4-bit calculator was invented. That was the first thing came into picture. And later on, only you have so many processes people worked on, and so many other inventions came into picture. Okay, so BCD to 7 segment now, to display a value in your calculator. You are seeing, no, when you press a button, 0 button, na, immediately you are seeing the value in a display. Got it? So we are giving the value in the form of BCD. We human beings deal with the 0 to 9. So that is what your binary coded decimal, right? So what is binary coded decimal? The value comprising from your 0 to 9. So when we people will deal only with that. We will just enter the value in that form, and when you through a key or through any button, if you press the value, immediately it is displaying it. So how now? So for that there is a circuit you will be designing. So we will see in the later class. In today's class we will see specifically, because adders and subtractors are covered in your classroom. So today we will see the comparators, magnitude comparators. And generally, this is just like a refreshing your mind. How will you design any combination circuit? First, a verbal description about the problem. That is, whatever the circuit you need, the verbal description of it would be given. From the verbal description, that is the problem statement, you have to come out with your block diagram, which will help you to identify how many inputs and how many output variables from the block diagram, and you know the functions based on the problem statement. You can plot your truth table. Got it? So truth table is nothing but your pictorial representation of the function of, or the logical function of, any circuit. So the truth table will comprise your input versus output. So when I give a certain set of inputs, based on the problem statement function, based on the function given, we will produce the output. So we will plot it in a truth table in the form of zeros and ones, and thereafter with the help of the truth table, from the truth table with the help of K-map, we can obtain the simplified logical expression. So from the logical expression, you can come out with a logic diagram. So this is how you can implement any function or the law or the circuit you want to perform any specific logic in that. Okay, so how many steps? From the statement, block diagram, truth table, K-map, and then logic diagram. So simply remember this. So today we have to design a magnitude comparator. What is a magnitude comparator? From the name, you can easily identify what is this circuit is going to be. What is this? Could anybody answer this? What a comparator? What do you mean by a comparator? Kindly put it in the chat. What do you think a comparator would be? From the name, you can make a guess, right? Also, I've given for a few lines over there. What would be a comparator? What do you mean by a comparison? Comparator is nothing but a circuit which is going to perform the comparison between two, since the name clearly states the comparison between two magnitudes. Here, what are the magnitude levels available? Either 0 or 1, right? Those are the two input possible combinations of magnitudes a circuit could face in any digital electronics, right? So specifically speaking, this circuit is going to compare the input signal. Suppose if comparison now, always the circuit's input should be what? Two inputs. So both could be 0, both could be 1, one could be 0, the other one could be 1, right? Say yes or no. Could I see any answers over the chat? Could you post? I'm waiting for the answers. Guys, am I connected? Fine. At least you have answered for whether I am connected. Yes, I am connected. For your kind information, just remember a magnitude comparator is again one of your combination circuit which is going to compare the magnitude level of your inputs, right? Just make note of it. It is going to compare, just simply it is going to compare the magnitude levels of your input to that particular circuit. It will say, so comparison, out of comparison, what is the output you could see or what is the conclusion you can specify is, you can come out with the conclusion now, whether both the inputs are equal, greater or lesser. These are the three outputs. Am I right or wrong? So these are the possible comparisons or the analysis you could come out of your inputs with your inputs, right? So what are the types of comparators you're going to design now? Single bit, 2 bit and your 4 bit. Okay. So say suppose, for example, in your circuit, if I'm giving a data like this and if I'm asking you to come out with the answer, I'm giving a data A is equal to 0. If I ask, this is your B, right? Now I'm asking that compare these two set of inputs. This is one input, this is second input. I'm asking each input is of how many bits? 4 bits. Okay. So what is the decimal value of A? What is the decimal value of B? We human beings knows to compare just based on the decimal values. What is the decimal value for this, ma? That would be 2. What is the decimal value of this? 12. When I compare 2 with 12, how will you say, we human beings will compare and say A is less than B? Am I right or wrong? For some cases, you will come out, say suppose if I'm asking you to compare these two values and I'm asking which is higher and which is less. You just compare and tell me the comment on that now. How will you comment? You will say suppose this is A, this is B again now. If it's a decimal value now, it is easier for us to tell, right? This is 8 plus 2, 10. Right? What is the decimal value of this? This is 8. So we will obviously say that A is greater than B. Am I right or wrong? And if I'm giving a data like this, two sets of data, and if I'm asking you to compare these two sets of inputs now, what would you say? This is also 14 and this is also 14. So A is equal to B. Am I right or wrong? Am I right or wrong? At least for that say yes. So if it's a decimal value now, it is easier for human beings to understand. Whereas how this analysis would be done by a circuit, which doesn't know to perform on its own, but it will perform when we instruct certain things. So what a circuit would do now, it will compare, say suppose, eventually when I give the inputs A is equal to, say suppose, I will take the first set of inputs. Say suppose if I take the, so I've given examples for A equal to, less than and all in a decimal value. Now how a circuit would compare and tell you that it is lesser or greater. What a say suppose, just a minute. I'm giving a data like this. A is equal to 1010 and B is equal to 1011. Tell me immediately how a circuit would be comparing. So even without converting into a decimal, how you will guess which is greater than which, or which is lesser than which, or is it equal? Just by saying it, we can say it is not equal, because whatever is present in A is not present in B. So these two inputs are not equal. I'm damn sure about it. But if I ask you to compare and say without converting into decimal value, how will you compare and tell me? First, you will see the MSB bit. This is 1. This is also 1. Second, next to your MSB bit, what is the next bit? 0. A is 0. B is 0. So both are same. Okay, 2 bits are same. Next, you will compare. A is 1. B is also 1. So till 3 bits, all the 3 bits starting from your MSB, all the 3 bits are the same. Next value, the last bit is going to say or speak or decide which is greater, which is lesser. Here A is 0, B is 1. Am I right or wrong? A is 0, B is 1. So which would be greater? Obviously this would be greater. This value would be greater, since because of this bit alone. Okay. So now tell me the decimal value of this. So this is how the circuit will also analyze bit by bit. So bit by bit analysis the circuit will do for a, or inside your magnitude comparator. Okay. So we have to instruct this. You do like this. So for that we have to come out with a truth table like that. So if we plot the truth table like that, we can plot the K-map. From the K-map, we can come out with the expression and finally with the logic diagram. Did you understand? So now plot and see the decimal value of this. This would be 10 and this would be 11. So this is greater. So so instead of saying B greater, always in magnitude comparator, remember you will have only two inputs. Only two inputs. What are the inputs? A and B. Two inputs. What are the inputs? A and B. How many outputs? Only three outputs, as like your half adder, full adder. There is no change in that. What are the outputs? Always A greater than B, or A less than B, or these are the different outputs. What are those outputs now? A greater than B, A less than B, or A equal to B. So these are the possible outputs a circuit, which circuit a magnitude comparator could have. Okay. So always remember two inputs, three outputs. So this is what I have come out with a block diagram. Till this, did you understand? Just put a thumbs up so that I can understand. Till this, can you people understand? Guys, kindly, because I don't know whether I'm connected or not. Thank you, thank you. So now you know what a magnitude comparator circuit would be. So what it would be in we are going to design the circuit. Still we are not into the circuit, but we have identified from the verbal statement based on the function we need the circuit to perform. We have identified how many inputs, how many outputs. Did you get it? So this is the block diagram. So step 1, the verbal statement. So now we are going to design a 2-bit magnitude comparator. Always two inputs. How many? What are they? A and B. But how many bits are they are going to be? They could be single bit. A could be single bit, either 0 or 1. B could be either 0 or 1. We can compare each and every bit. That is one condition. Say suppose A is of 2 bits and B is of 2 bits. So that we call it as a 2-bit magnitude comparator. And if it's a 4 bits, so this is an example of your 4 bit. With a 4 bit only I have taught you. Okay. So now we are going to start with a 2-bit magnitude comparator. So how many inputs? 4 input signals. 2 will be categorized under the tag A0, A1, and 2 other would be categorized under the tag B0, B1, because we know always 2 inputs A and B and each of 2 bits. So those bits we have denoted with 0 and 1. And how many outputs? 3 outputs. Equality function stating equality function, greater than function, and less than function. Okay. So these are the functions. So with this block diagram, we will move for the truth table. Sorry. So if it's a 2-bit magnitude comparator, how would be a truth table? As I've stated already, how would be a truth table? This is as I've told you, truth table is nothing but your pictorial representation of your any logic function of your circuit. So you know the function. What is the logical function it has to perform? This circuit has to perform. It has to compare. What are the things it has to compare? Now, two input signals, which I will write it here. Two input signals. It has to compare two input signals. What are they? A and B. So these two bits are A0, A1, and then you have your B0, B1. Okay. You take it as this as A0, A1, and this as B0, B1. What are the possible combinations of your comparisons could be? Because I am designing a general purpose circuit. If any number of person comes and tries and works with the circuit with any number of combination of inputs, it has to produce the output. So I have to design a circuit with every possible combination of inputs. So if it is a 2-bit always what are the possible combinations it could occur with 0 0 0 1. That means what? One could be 0, the other one could be 0 or 1. What is the next combination? If one input is 1, the other input could be either 0 or 1. So this is how I say a 2-bit is nothing but it could come out with 4 possible combination. So what I'm going to do is here each of the 2 input signals are of 2 bits. Each of the signals, who are the signals, input signals? A and B. Both are 2 bits. So this will have 4 combination. So the 4 combinations of A should be compared with 4 other combinations of B. So what I'm going to do is First I'm going to compare. So what is the decimal value of this? This is 0, this is 1, this is 2, this is 3. So I'm going to compare first 0 value of A. What is that? 0, 0 with B value of 0, 1, 2, 3. Did you get it what I'm trying to say? First I'm going to compare 0, 0 of input signal A with every combinations of B. B is of again 2 bits. What are the every combination? 0, 0, 0, 1, 1, 0, 1, 1. So first I'm comparing. So decimal value is what? I'm comparing 0 with B values of B. What are the B? 0, 1, 2, 3. From the decimal value, you could directly tell me which is going to be equal, lesser, greater, everything. But how a circuit has to work, that we are going to instruct. So, how many possible combinations of output you have? A greater than B, equal to B, less than B. So, now compare. 0. Here A is 0 of value, decimal value 0, and B is also 0, 0. So the decimal value of it is what? 0. So both are 0. So that means what? Equality function should be high and it should produce the output of A equal to B. The other remaining two has to be disabled. So that means what? 0. It should not produce or show any output. So I am forcing it to 0. Okay. When a input of A is equal to 0, 0 and B is equal to 0, 1, which is higher or which is lesser? A is 0, B is what? 1. So A is less than B. The output of the circuit has to be like A, indicating A is less than B. It should not indicate A equality or A greater than. So these two functions has to be disabled. It should not show the output. It should not produce the output. These two. Okay. Whereas this should produce the output when this combination encounters. Next combination, when A is 0, 0, B is 1, 0, again A is less than B. For this combination also, A is less than B, output should be enabled and every other output has to be disabled. We are forcing only through the truth table, we are going to instruct the circuit. Okay, this is how the circuit has to work. How? Just by enabling high and low. So we are deciding, we human beings, we design the other deciding factors for this circuit. How am I deciding? Because I know. Okay. And similarly, if A is 0, 1, 0, 1 means what? The decimal value is what? 1. What would be the possible combinations 0 of B? 0, 1, 2, 3. So a value of 1 should be compared with, if say suppose if anybody giving the input like any with any one of these combinations now, it should be able to produce the output. So that is why we are writing the truth table for all the possible combinations. Okay. So if suppose a circuit encounters with a value of 1, A equal to 1 and B is equal to suppose 0 now, it should be stating or highlighting A is greater than B, because A is 1, B is 0. Why am I saying 0 decimal value 0? Because 0, 0, 2 bits are 0, 0. So the decimal value is 0. Say suppose if the value of A is 1 and B is also 1, then the circuit has to produce the equality function as high output. Then if A is equal to 1, if the circuit encounters with a input like A is equal to 1, 1 9 0 1, okay, B is equal to 2 na, suppose if it encounters with 1 0 1 0 9 2 1 8 4 2 1, that code. Okay, so 2. So it is obvious A is less than B. So this has to be enabled. So likewise, I'm comparing for the value of 2, 3 of A and with every possible combinations of B. I'm making one constant and comparing with all the four. And I'm repeating, next I'm selecting second case of this and I'm making the comparison. And I'm taking the third case and I'm making the comparison. And I'm taking the last case. So likewise for 4 cases, you have to compare with every other 4 cases of the B input, and you have to plot the output. So now I have the final truth table. For truth table, you should write only alone these A naught A1, A B naught B1, A greater than B, A equal to B, A less than B. For explanation purpose, I have given all these decimal values. You need not mention the decimal values. Okay. Till this, did you understand? Till this, did you understand? Any doubts? Now put it in the chat box. Any doubts? Now kindly mention in the chat box. Else I'll proceed. Shall I proceed? Thank you. Thank you. Okay. Okay. So this is the case. So likewise, how many output they give, you have to compare with of every other possible combination with the other input. Okay. So for this case, truth table is over. Next step is what? K-map. So how many outputs? So based on the number of outputs, you should come out with the number of K-maps. So how many outputs are there? Three outputs. Three outputs na three K-maps. What structure K-map? So that has to be decided by the number of input bits, total number of input bits. You should not take only A and B. A is of again how many bits? 2. So altogether how many number of input bits? 4 bits. So if you have 4 bits now, then inputs is 4 and output is 3. So you should have 3 K-map structures, and what structure you should make use of? Sorry. You should make use of 3 K-maps, and what structure K-map you should choose? 4 input variable K-map. Okay. So 4 input variable K-maps has to be taken, and you have to plot and you have to start doing it. So what is a K-map you would draw for A greater than B? How you would draw A greater than B? No? 0 0 sorry 0 1 1 1 1 0. Here also 0 0 0 1 1 1 1 0. So this will be your, so always I've instructed, if you want to plot the K map now, just take as such in this. However you have plotted the table, say suppose some people will plot this as A naught, and some will plot this one as a A1. Okay, here we have taken it as A1, A naught, B1, B naught. As such, you just plot it here, A1, A naught, B1, B naught, as such. Okay, so if you go and continue with that now, that would be easier for you to plot, because why am I saying now? Look at the total value of, instead of splitting into two bits, you take the total value of this. This looks like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Look at the rows, total rows, 8, 9, 10, 11, 12, 13, 14, 15. So starting from the decimal value 0 to 16, sorry 15, you have the values which you can straight away plot it. That is why I'm telling you. Okay, so now I have to plot and take the output of a greater than b. So a greater than b equal to, that is a function, right? In certain functions we will use to plot it as f is equal to and y is equal to. Here a greater than b. So what is the first value? Because straight away we know what are the possible combinations straight away. Just now I showed you starting from 0 to 15. It is in the order. So start plotting it. A greater than b na 0, 0, then 0, 1, 2, 3. What is 4? 0, 1, 2, 3. 4 is 1. Okay. 5, 0, 6, 0, 7, 0. And 8 is 1, 9 is 1. Again 0, 0. Right? What is this? 15 is 0, 14 is 1, and 14 is 1, 13 is 1, and 12 is 1. Okay, 8, 9, 10, 11. Okay, correct. So you have a plot like this. So if you map it continuously, it would be easier because you know there is 0, cell values are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Because, because you know already, right? We have done it in unit 1. So now we have plotted the values of A greater than B. Now we have to group it. Always, if it's a four variable, now aim for 8 cells. 8 cells are not high. So next is 4 cells. Quad is possible. Look for that. Yes, it is possible. Where now? Here. You have a quad to be possible. Here you will group it. And then which are the min terms left out now? This and this. So for this, which are the adjacent cells? This one, and this one, and this. Only this a pair could be made, and a pair. That's all. So write the expression. What is the expression? A1, sorry, A1. So what is the quad expression? This is quad A1, and which is common here? B1 bar. A1, B1 bar plus this pair, which is common? 1. So what is 1? A0, and this one is what? B1 bar, B0 bar. And for this pair, this is A1, A0, and which is common in the columns? B0 bar. Right? So what is the expression for A greater than B? For that to be enabled when the inputs are given, then this is the logical expression. So if you draw the circuit for that, you will get the circuit for A greater than B functionality. Likewise, you have to plot the next K map. Got it? So similarly, A equal to B, A less than B. If you plot it, you will have the expressions as we have it here. In your books, just have taken the snapshot of your book. Look at this. Here they have taken A1, A0, B1, B0. So you plot it. So first K map we have solved it already. A greater than B. Likewise, if you plot the values of A equal to B, you will end up with a mapping like this because no min term will be grouped here. Look at the minterms, it is diagonal. So diagonal na you can't make any grouping. So individually you have to mark it as a single. Okay, single group. So round it like this and write the expression. What is the expression? Both the row and the column expression would be contributing for each cell. So you will have 4 variables for all the 4 product terms. So again you have to simplify the expression taking out the common terms. If you take out the common terms, finally if you simplify as we did for your half adder and full adder, here also even after some times, got it? Even after sometimes making a grouping in your K-map with the help of K-map, again you have to apply certain mathematical rules so as to get a very simplified expression, because we have the special derived gates only for these things, because instead of making use of OR gate, inverters and 4 AND gates, I can just simply make use of 2 XOR gate. XNOR. You can write it like this or like this. Okay. So this whole expression could be implemented, that is the to A equal to B. So as to identify when any two input bits are equal, na, it could be done with the XNOR. What is your XNOR? You know the truth table of your XNOR. What is that? When two inputs are 0, 0, 0, 1, 1, 0, 1, 1. This is the truth table of your XNOR gate. What is the XNOR? Y is equal to, when both the signals are same, you will have the high output. And if you have different inputs detected, then the output of the XNOR gate is what? 0, 0. So this is the truth table of your XNOR. So even when you simplify and see, you will get the same thing. Okay. And also you know the logical expression of XNOR. What is the XNOR logical expression? Y is equal to A bar B bar plus AB. Okay. Who are contributing high? Which are the signals high? This is high. It produces the output high when A is 0, B is 0. That is why we have written it as A bar B bar, or it produces the output high, the XNOR. Okay. It produces the output high when both the inputs are equal to 1. So that we represent it with A into B. 1 means what? Without complements. 0 na with complements. So this is the truth table of XNOR. The truth table of XNOR, from the truth table you can also write the logical expression A bar B bar plus AB. How na? From the truth table only we are writing it. Since we are ending up with certain functions like that, look at this function here. You have A naught bar B naught bar plus A naught B naught. So simply you can replace with A naught XNOR of B naught. This is a symbol. This is a symbol of your XNOR, and this is the symbol of your XOR gate. Okay, do remember. You have to circle it. Put a plus and you have to circle it. Only then it becomes XOR. Here XNOR. Okay. So just by taking out the common terms and rearranging, you will get this set of expressions. Similarly, if you plot for A less than B, you will get the mapping like this, and if you group it, you will have one quad and two pairs. Since you know already your K maps, I'm not going deep into it. Okay. So when you map and write the expression, you will end up like this. So now I have the logical expression for 3 functionalities, and that too to compare 2 bits of 2 input signals. Okay. So now from the expression I'm going to just draw the circuit diagram. This you know. Okay. For equality function, 2 XNOR gates, because 2 bits. Okay. A naught, A1, B naught, B1. So you have 2 bits. So A naught, B naught for one XNOR and A1, B1 for next. It will compare. When both are 1, only when both are 1 you have output high. I mean, only when both the bits are equal, you will have output have to be high. So that is why AND gate. This bit has to be equal and this bit has to be equal. That is why, look at the word I am making use of, AND. So product term. Wherein for A greater than A less than, if A naught is greater than B naught, or A1 is greater than B1, or this A naught is greater than B naught, or A1 is greater than B1 or A naught is greater than B naught. You can have the, so this is a OR condition. So that is why I'm making use of a adder. Got it? Plus. Did you get it? So you should make use of a OR gate here. Here you should make use of a AND gate. So this is how you can just simply denote your expression in terms of your logic diagram. So this is your 2-bit magnitude comparator logic diagram. Hope you would have understood. Yes, AID students can join. No issues. Syllabus are the same. Okay. So actually speaking, you should have started with your single bit. So that is why I had earlier the single bit. So 2-bit you understood how to design. Suppose if a single bit magnitude comparator is asked to design by you, by a customer or by a client, how and what will you do? So if a client is asking you to, as a design engineer, design and give me a one bit or single bit magnitude comparator, now how will you do? You know the block diagram. A magnitude comparator, put it in a, I'm going to come out with a circuit. So that is your block. How many inputs? Always two inputs. What is that? A, B. How many bit A and B is? One bit. One bit. A is going to be one bit. One bit na, that bit could be either 0 or 1. B could be either 0 or 1. Okay. So how many inputs? Two inputs. How many outputs? Three outputs. Because based on three functions you can denote the comparison. What is that? A greater than B, A less than B, A equal to B. So that is what I have plotted in your truth table. So this is your truth table. Okay. Since just I randomly picked it. Actually, you should write the statement, verbal statement, what your designer is, client is asking you to do. That is your problem statement. Step 2 is what? Block diagram. So here I've given the block diagram of it. Okay. Step 3 is what? Truth table. So this is your truth table. Step 2 is block diagram. Step 3 is truth table. This is your truth table. How many inputs? Two inputs, A and B. When A is 0, B could be 0 or 1. When A is 1, B could be 0 or 1. You have to compare all these possible combinations. While comparison, the output could be either greater than, lesser than, or equality. If both A and B are 0, now who has to be high? Who has to indicate the output? Only through A equal to B, we have to signal the output. Okay. And the remaining two has to be disabled. These two should not work. So that is why I made 0. When A is equal to 0 and B is equal to 1, who is high? B is high. So that means what? A is less than B. So that should indicate the output. Okay. And the remaining two functionality should be disabled. Only this functionality should be enabled, indicating the A is less than B. And A is equal to 1 and B equal to 0 now, the circuit has to indicate the functionality A greater than B and remaining two disabled. Okay. Likewise, when both are 1, 1, then A equal to B should be enabled. So the circuit should be signaling, okay, what you have given the inputs are equal. Okay. So now the truth table is plotted. If plotted now, what is the expression? Could you map the K map for this? How many K maps? How many K maps you have to plot for 1 bit magnitude comparator? How many K maps, ma? Kindly answer so that I can understand. How many K maps do you need to come out with the expression? Here simply I've written it. But actually speaking, how many K maps do you need to plot this single bit magnitude comparator? Come on guys, I have taught you 2 bit. So you should be able to answer for single bit. How many K maps? Kindly answer. Am I audible? Make a guess, no issues in that, right? Okay. As you all know, the circuit has to indicate the for either of the 3 outputs. So how many outputs are there? 3 outputs. A greater than B, A less than B, A equal to B. So you need 3 output K maps for, so here you need 3 K maps. What structure K map you should need? Go for two two variable K map. What is a 2 variable K map? This is how it look like. So how many? 3. So A less than B, what is the K map? A, B. This is 0, 1, this is 0, 1. Okay. When both are 0, it is 0. So for this I am plotting the K map. A less than B. When both are 0, na 0. When A is 0, B is 1 and na 1. Because B is greater, right? When A is 1 and B is 0, na 0. And when both are 1, na 0. Likewise, A greater than B, na for this is A, this is B, 0, 1, 0, 1. Here what? 0, 0, 1, 0. A is greater than B. Okay. Similarly, for this A equal to B, na, here A equal to B. So which are the conditions you will have when both the inputs are 0, 0 high, and when both the inputs are high, na, you will have equality function. For remaining cases, it will be lesser. So what is the grouping here? Only single, here also single, here also, because it is diagonally present. So you will have A less than B is equal to what? A less than B output is what? A bar B. A less than B is equal to A bar B. A greater than B function is equal to output function is equal to what? A B bar. And what is this grouping? A equality function to represent, we have A bar B bar plus AB. So what is this expression again? You can simplify. What is that? X nor. So simply you can replace. So always remember, to find the equality function, X nor gate is used. Okay. So simply you can write it like this. So this is also equivalent to this. So simply you can draw the logic diagram. So this is the final step. Okay. So you can draw it individually like this, or you can tap it like this. You can put A bar, B, B bar. This is B. And from here you can tap it. Okay. Sorry. that is A, right? A, B naught. Okay, and this is A, B bar, A, B bar, and here A bar, B naught. Okay, so like this you can draw. This is also right and that is also right. Okay, so first you have to always come out with a statement. Second, your block diagram. Third, K map, sorry, truth table. This is your truth table. Okay, and from the truth table, K map has to be plotted. From the K map, you have to plot the, or you have to come out with the logical expressions like this. The logical expressions. Okay, for the three functions, output functions. What are the three output functions? From the functions, you can straight away draw the circuit diagram or the logic diagram like this. Okay, so this is a very important topic actually speaking for your exam. Okay, so I've scribbled. Simply you can see a fresh one. Like this you can draw the final diagram. So this is your final logic diagram. It has to be like this. So in today's class, in today's session, we have discussed about single bit or the 1-bit magnitude comparator, 2-bit magnitude comparator, right? So now a very important question is always they will ask in part B, that is for 13 or 15 marks, you can expect 4-bit magnitude comparator, okay? They won't ask a easy question. It's a 4-bit comparator. Okay, 4-bit magnitude comparator for your this is an extra information, like it is available in that, all the things are available in IC form, and IC 7485 is your 4-bit magnitude comparator. In your laboratory, if they ask you to do this experiment, you can go pick up this, and this is a pin diagram of it. You can give the input connections and you can take the output and see. Okay, just for that purpose I just brought this, but for designing, for theory exam point of view, do remember, give the statement like this. Let us consider the two binary numbers A and B with 4 digits or 4 bits. Okay, write the coefficients. What is the thing you are assigning with? How you take the variables A naught, A1, A2, A3, B naught, B1, B2, B3. Okay, some people will take it as a XY. That is also right. So here, so you have to make it legible that and clear that to the examine evaluators what variable you are making use. Okay, that you have to make use of it, and then after that you have to draw the block diagram. You know already, since I have taught that, I am not coming out all this, but still I will write it. How many inputs? Second step is what? Block diagram. It is a 4-bit magnitude comparator. Write it. This is a block you are going to design. Magnitude comparator. And how many outputs? Always 3 outputs. A less than, greater, equal. Okay, how many outputs? 4. Sorry, how many inputs? 4. So 4 inputs, in the sense, actually speaking, how many inputs now? Each 2 inputs, but each of them are how many bits now? 4 bits. Altogether you will have 8 bits. Here you can directly write it as A0, A1, A2, A3, A4 till like 8 things you can bring it, or simply you can denote with A like this, and you can put it as a ratio from A0 to A3, B0 to B3, a kind of symbol like this, and you can write it. Okay, so that is also okay, no issues. So next step is what? Truth table. Truth table for 4-bit magnitude comparator. Imagine for 2-bit itself you had 16 possible combinations. For 4-bit, how many possible combinations you will have? 15 combinations of A should be compared with 15 other combinations of B. So how many combinations you have to check? around 30 combinations in your paper you have to come out, which is a very tedious job. Instead, I will tell you a hint. Like this you can plot the truth table. So 4-bit magnitude comparator, more than 4-bit na, this is how you have to follow. 4-bit na, like this you have to. 5th bit na, then one more column will be there. 6th na, one more column. Okay, just you should keep adding. Outputs doesn't change. So how will you draw the truth table now? Before coming with a thing, I'll just plot it how we can do it. So you know, how will you compare if I ask you to, if a circuit is provided with this set of inputs now, I told you already, bit by bit it will compare. How we human beings will compare? First you will look at the MSB bit. Why we are looking at the MSB bit instead of LSB? Now LSB least value. It is not going to decide the nature of the circuit. So look at the MSB bit. MSB bit high. Who is carrying the highest value? Here MSB bit for A and B, it both are high. So we can't decide with that bit. So what is the bit I'm going to assign? This is A0, A1, A2, A3. This is B0, B1, B2, B3. So with the help of A3 and B3, if you compare those two bits, can you decide which is greater, which is lesser? Which input is greater or which input is lesser? You can't do that because both are equal. But as a whole, if I look at, it is not equal. So we start comparing bit by bit. Next bit is what? A2 is high, B2 is low. So from this itself, the circuit will stop and will not proceed with this. From this itself, it will decide A is greater than B. So bit by bit comparison, whether A3 and B3 are equal, lesser, greater, it will check. Based on that, it will produce the output. Next bit, it will check. Similarly, the next and the very next. So bit by bit, if you compare, say suppose, so you have to plot the values like this. For that I have the mapping. Just a minute. So now this is how the columns has to be. First column is what? So your first column is what? A3, B3. Okay. Next is what? A2, B2. This is how you have to write. Comparing the inputs bit by bit combination. Okay. So first you will check irrespective of the second, first and the LSB bit. Irrespective of these three, I least care about it. If A3 is greater than B3, immediately the circuit will produce the output high. A is greater than B. It won't compare, or we don't perform the analysis of this. It is not necessary because A3 bit is high enough, then that will be the highest value. What is the A bit? If A3 is high enough, say suppose this is an example for this case now. Here look at A and B, A3, A2, 1, 0. Here B3, B2, B1, B0. Look at this. Though 3 bits are high in B, but the value doesn't contribute for that because the MSB bit, which carries the position value of what? 8 is high. Wherein even if all the 3 are high, what is the positional value? When we add it together, we have the digit 7. So since this is high, this takes the value. So A is greater than B. So just with the help of, when I compare A3 and B3, just from that I can decide immediately and produce the output instead of checking for these things. I don't care about this. So that is why this is a don't care symbol. I don't neglect. I neglect this. I neglect this. Okay. I neglect the comparison of these three. Next, suppose this could be 0, this could be 1. If that is the case, then this is the highest value because MSB bit is what? 8. So 8 plus 7, 15. where even if these are going to be 0 or 1 or any possible combination, 3 bits could be of 7 possible combinations. Even if it is of different combinations, like possible 7 combinations, if B3 is high, na high da. So ignoring the remaining 3 bits analysis, just from the first bit MSB bit, I will decide whether A is greater than lesser just by seeing the value and produce the output, respective outputs. Suppose if both are 1, suppose A is 1, here A3 is 1 and B3 is 1, and say suppose this is an example I will take. Say suppose this is a and this is B now. I'm comparing A3 and B3, both are equal. Immediately what I'll do, I'll check for the next bit. What is that? A2, B2. I will check whether this is lesser or greater. Now A is lesser, so corresponding value would be high. Suppose if this is both are equal now, I will go and check for the next bit at that time itself. So when this bit is equal, I will check immediately whether lesser or greater. Okay, who the next bit, irrespective of the A1 and A0. I neglect that. Just based on these two, I can decide whether A input signal is greater or B input signal is greater. Okay. Suppose even that second bit is high, even that second bit is A2, B2 is high enough, then I will go and compare whether third bit from the third bit from MSB is what, this one, whether the third bit is greater or equal or lesser. Okay, this is what they have done, whether the third bit is lesser. So suppose lesser greater na, we can come to the conclusion. If it is, that is also again equal na, then immediately at that stage itself, look at that where I'm plotting it. At the next I'm not doing it. Immediately at that case itself, in that case itself, I am checking for the condition whether A naught is greater than B naught, A naught is lesser than B naught, A naught is equal to B naught. Okay, again based on that I will produce the output functions. So with this you can stop the truth table. You need not go and do the cascading inputs. Cascading means you have to assume clubbing all the 4 bits together, not bit by bit. So far what we have done is a bit by bit analysis, whereas the remaining two is both could be like cascaded together. You can take the value and then you will compare the A with B. Okay, so that is why they have plotted again, but no need, you can stop with this. And from the truth table, just again the same way you have to plot the, actually instead of plotting K map, because how could you plot the K map? Because here you have 3 outputs, A greater than B, lesser than B, equal to. Okay, va. So 3 outputs. Ana 3 came up da. But how many inputs? 1, 2, 3, 4, 5, 6, 7, 8 inputs. 8 input K maps la. Then you need how many? 5K you need 2 chart, right? 6 you need 4. Imagine 7. Twice of it, it will just increase. So you can't do it easily. But instead, you know the function. From this table, straight away you can write the logical expression. So now, when and all A is equal to B, when and all A is equal to B, single bit நீங்க பாத்தீங்க, single bit, 1 bit magnitude comparator, what is the gate used to detect whether A is equal to B, X NOR, right? So how many bits you have? 4 bits. So assume it as when A3 is equal to B3, or when A2 is equal to B2, or A1 is equal to B1, A0 is equal to B0, you can make use of, or you can again simplify and write it as, you can assign with some variable x3, this is equal to x2, this is equal to x1, this is equal to x0, and what is the gate used to detect? X NOR gate, right? So XNOR gate now I can symbolize the equality function like this, right? 3b3, you can rewrite. Did you get it what I'm trying to say? B1 again, A naught XNOR B naught. So the same equality function could be detected with 4 XNOR gate. So which I have assigned it as x3, x2, x1, x0 for each and every bit of combinations of A and B. Okay, I'm assigning it. So this is the logical expression of your equality function. Equality function of the first MSB bit, second from MSB, then third from MSB, and the LSB bit. Did you get it? So 4 XNOR gates to find out bit by bit equality. So which I have assigned with the variable named x3, x1 and x3, x2, x1 and x0. So the equality function, this is how you can write. Next, A less than B, A greater than B. How will you come out with the expression? How will you come out with the expression? Say suppose, I will write it simply, just interrupt it. Till this, did you understand? Any doubts now, put it in the chat box. Till this, if you understood now, say yes, understood. So what could be the expressions for A less than B? Now top I'll write it. A less than B. What would be the expression for the function A less than B? So this is where you have to look this combination. This column I'm going to write the expression A less than B. For this I'm going to equality. What is the expression? X3, X2 equal to X1 is equal to X0. I have written it already. For A less than B, what is that? When and all it is high? It is high when don't mark all these things in your exam paper. This is for your reference while teaching and doing it. So when it is high when A straight, you just observe when A3 is lesser than B3. A3 is lesser than B3 na, that means what? Here high and low is what? A3 could be 0 and B3 is 1. You can write like this, no? Or when it is high, it could produce a high output for the condition. What is this condition? When A3 is equal to B3 and it should be only when this is equal, I should check for this and I'm producing the output. So these two conditions has to be this and this condition. So A3 is equal to B3 is what? X3. Simply I can write it as X3 when the condition is X3 and A2 is less than B2, this output could be prevailed. This could be produced. Okay. Next, or it could produce the output. See, just by saying the words, I'm writing the expression. From the problem statement, I'm stating it. You can come out with the expression. Next, it is high when A3 is equal to B3 and it is high for the condition when A3 is equal to B3 and A2 is equal to B2, that we represent with X3 and X2 and operation. And what is the other condition? When A1 is less than B1. A1 is less than B1 na, A1 bar B1. And again when it is high, when for this case. So till this you have to write it. What is the other condition? When x3 is equal to and x2 is equal to and x1 is equal to and a naught bar b naught. When a naught is less than b naught. So you can till this you can draw the truth table. You need not draw the truth table for these two. This is for cascading. That is as on whole if you take the output when all are equal. You have to go for this condition. You need not do that. Don't get confused. Till this you stop it. Okay. So now as like a less than b, if you start writing for the a greater than b, what would be the expression for the function a greater than b? Look at which are the terms, min terms high. Here this is high. Here this is high. This is high. This is high. This is high. And this is high. So when A3 is greater than B3, that means A3 is high, B3 is low. Or when it is high, or when it is high for this condition. What is that? Or A3 is equal to B3 and that in short I'm writing it as a x3, that equality function, because I have assigned it already, and A2 is greater than B2. Or when x3 bit is equal, A3 is equal to B3 and A2 is equal to B2 and A1 is greater than B1, this output is high, greater than. Or when the third bit is equal and second bit is also equal and the first bit is also equal, and when the condition A naught is greater than B naught prevails, the output is produced. So these are the possible conditions the circuit A greater than B circuit could be producing the output. Likewise A less than B. So we have stated A less than B, A greater than, A equal to. Okay. So now look at the diagram for this. So this is how the expression comes into picture. If I show this, you won't understand. That's why I wrote it there itself. Actually speaking, you have to write the expression. Here instead of x3, x2, x1, they have assumed it as a e3, e2, e1. The variables could be different, but you have to proceed with the same variables. Okay. So this is how you have to write it. So this is the x, or with the inversion also you can represent a x nor, or simply you can write it like this. Simply like this, you can straight away denote the expression. So any book you follow, the concept is the same. That is what I am trying to say. So this is the final logic diagram. From the expression straight away draw the, for equality again, since it is 4 bits, you will have 4 XNOR gates. And from the expressions of A greater than B, A is greater than B, then all the B inputs should be complemented. If A is less than B, all the A inputs should be complemented. That is what simple, actually speaking, if you understand. Okay. Did you understand the 4-bit magnitude comparator? So any doubts? With this, your magnitude comparator topic is over. Any doubts? Kindly ping me a message. Else we can wind up. Yes, thank you. Any doubts? Post it at the chat. Thank you, ma.